So hello everyone, welcome back to lecture series on aerospace propulsion. So in the previous lecture, we were discussing about the cycle analysis of a turboprop engine. Okay, so turboprop as well as turbofan engine we have discussed. So if an inlet design parameters are given, how we can find out what is the flow property, that is pressure and temperature at the each and every station of our gas turbine component. Ultimately, how we can calculate thrust as well as the performance parameter of an gas turbine engine, how we can calculate, that's what we have discussed in the previous lecture. So with that, your first chapter is over. So today we are going to start the second chapter. Okay, so the second chapter onwards, as we have already mentioned, so the different components we are going to discuss, that is components of our gas turbine engine. As you know, what all the components of our gas turbine, it starts with the intake, and then we have compressor, and then we have the combustion chamber. After combustion chamber, we have the turbine, and then we have the nozzle. Okay, so in this chapter 2, we are going to discuss about the inlet as well as the combustion chamber. Okay, so before going to the combustion chamber, today we are going to discuss about a brief introduction about the intake. Okay, so what is that we are going to see in this lecture is that brief introduction about the intake and what is the requirement of intake, that is why do we need an intake in a gas turbine engine. Okay, and what is the function of this intake, and we are going to see about the types of intake, that is we have a subsonic as well as supersonic intake. So first we are going to start with the subsonic intake. Here we say either intake or inlet, both have the same meaning. Okay, so after discussing about the subsonic intake, we are going to see about the how a flow is passing through an intake and what is happening and what is the problem we have in the intake, that is stall. How does the stall is happening and what is the consequence of stall happens in your intake. That's what we are going to see, and then later we are going to see the most commonly used, that is pitot type intake we are going to see, and their classification we are going to discuss. Okay, so where we are using a particular type of pitot intake and all we are going to discuss, and last we are going to see the operation, that is different operation modes of a subsonic intake. Okay, so let's start with intake. What is this intake, or what is the function of your intake? Is that basically the purpose of your intake is to supply the mass flow rate or required amount of mass flow rate to your engine irrespective of the operating condition. So what is the meaning of operating condition, or to be precise, flight envelope? For example, if an aircraft, say, and gas turbine is fitted within an aircraft, okay, so during your start, that is during your ground, your aircraft is still, okay, during that time also the intake has to supply sufficient amount of mass flow rate to your engine. Okay, and once it starts moves, its velocity getting increased, and during your takeoff it is experiencing the different inlet condition, and after taking off it will go to the cruise altitude. So once it goes to the cruise altitude, there we'll have a different flight condition, and once again your aircraft will start descent, that is it will land. So we have a different situation or different flight envelope or different operating conditions of our aircraft. So based on that, your inlet also has to adjust according to the flight condition and supply the required amount of mass flow rate at the required speed. Okay, so that is the purpose of your intake. So what is the basic or foremost requirement of an intake is that first it has to supply sufficient amount of mass flow rate with the least amount of loss in the total pressure or stagnation pressure. In sense, in an aerodynamics, okay, any process you take, that is going to be always, there is going to be an increase in entropy, meaning is there is a loss is going to happen, right? Same, if I'm going to keep some solid object in the incoming flow field, what is going to happen? It is going to produce certain amount of loss. Similarly here, since it is an intake which is made of a solid wall, when the flow is passing through this intake, there is going to be a certain amount of loss. So the first and foremost requirement of your intake when we start designing is that it should have a least amount of total pressure loss. That is, it should have a like maximum pressure recovery factor. So what is the meaning of pressure recovery? In sense here, it is basically ratio of P02 by P01. That is, it should be equal to 1, but we won't be able to get equal to 1, but it should be close enough to the 1. And second one is that irrespective of your operating condition, you should produce the sufficient amount of mass flow rate without choking. So these are all the two basic requirement. Any intake, whether it is a subsonic intake or supersonic intake, it has to satisfy. Okay, so as I mentioned previously, so first we are going to discuss about the subsonic intake. Okay, so what is this subsonic intake, or what exactly this subsonic intake does is that, so subsonic intake means basically an intake or inlet of an engine which is fitted in an aircraft which is going to fly in the subsonic region, or that is subsonic Mach number region. You know, right? What is the Mach number of your subsonic flight? That's close to up to Mach number 0.8. We call it as a subsonic. So 0.8 to 1.2 is transonic. So subsonic means your flight is going to be flying less than this 0.8. So obviously the flow encountered by your intake is also going to be subsonic. That's why we call it as the subsonic inlet. Okay, subsonic inlet or subsonic intake. So if I say intake, so what is its function? As I mentioned previously, you see, intake, for example, we have a different operating condition, right? During your takeoff, it is having very low speed. During your cruise, it is having maximum speed, right? So during your takeoff or during your like cruise speed, the flow experienced by your flow experienced by your compressor should have a certain amount of Mach number. It should not exceed the Mach number. Okay, for example, for your compressor, the maximum Mach number to your inlet compressor inlet should be 0.7 and minimum should be 0.4. Okay, so why? Because when the flow is passing through the compressor, you know what is happening across your compressor. We increase the velocity of your flow, and by increasing the velocity, later on we are converting that increased velocity to pressure. So basically, we have rotor and stator in the compressor, right? So when the flow Mach number, if it is in the range of 0.4 to 0.7, when it is passing through the rotor, it won't produce the supersonic flow. Because if the supersonic flow is produced in the compressor, what is going to happen? You know, in a supersonic flow, even a small disturbance will create or result in a formation of a shock wave. So you see how complicated your compressor is that. If the shock wave is going to form, or if you are going to have a supersonic flow inside your compressor, which will form the shock wave, and you know the process across your shock wave is kind of like a non-isentropic. There will be a huge amount of loss will happen. So including your aerodynamic loss, if there is going to be a shock formation, what is going to happen? Further increase in the total pressure loss will happen. So in order to prevent that, what we do is that we limit the Mach number of the inlet of your compressor within this range of 0.4 to 0.7. Okay, that is for your subsonic compressor, your minimum Mach number range will be 0.4, and for the transonic compressor, the maximum inlet Mach number is going to be 0.7. Okay, so transonic means your flow will have sonic Mach number inside your compressor. That's what I mean by transonic compressor. Subsonic means throughout your compressor, your flow is going to be subsonic. Okay, so the purpose of your intake here is that, for example, if your flight speed is say Mach number 0.8 or 0.7, I am having a subsonic compressor inside. Okay, what is going to happen? I have to decrease my speed to that 0.4. Okay, so then only you won't have the supersonic flow inside your compressor. Okay, so irrespective of whatever the inlet Mach number, or your flight speed, you have to reduce it to this range of 0.4 to 0.7. That is the purpose of your intake. Okay, so here, so what is happening inside your subsonic intake is that's what we are going to see in this section, that is internal flow and stall in the subsonic inlet. Okay, so what is the meaning of internal flow and what is this stall in the intake in sense? You know, the process across your intake. Deceleration means what is happening? There is an increase in the pressure. So in the direction of your flow, there is a presence of adverse pressure gradient. You know what is the meaning of adverse pressure gradient, right? If the pressure in the direction of your flow is being increased, that's what we call it as the adverse pressure gradient. Okay, so across your intake, what do? We decelerate our incoming flow. So when this deceleration is going to happen, okay, so what type of shape we will use? We will use a divergence section, right? Because your flow is subsonic. That means if I want to decelerate my incoming flow, I should use the divergence section. So you know that, right? Area velocity relation from that convergent section and divergent section. For example, if I'm going to have a convergent section, this convergence section will act as a nozzle if my Mach number is less than 1. Same convergence section will act as a diffuser if my Mach number is greater than 1. Similarly, this divergence section means increase in the area. If the passage area is increasing, that's what we call it as the divergence section. Okay, so when the subsonic flow enters the divergence section, what will happen? Your flow will be decelerated. Your Mach number will be decreased. So Mach number decreased means what will happen to your pressure? Your pressure will be increased. Suppose if your Mach number is greater than 1, same divergence section will act as a like a nozzle. So, but since our flight speed here is subsonic, what is going to happen? This divergence section will act as a diffuser. That is, this intake will behave similar to that of an diffuser. You know what is happening across your diffuser? If the flow across a passage is being decelerated, that passage what we call it as the diffuser. That is, your velocity will be decreased. Okay, your pressure will be increased. So, when this velocity is decreased and pressure is increased, what is going to happen? The flow momentum is getting reduced. Okay, so if the flow momentum is reduced, means right? Since this intake is made by a solid wall, whenever a flow is moving over a solid wall, we will have the boundary layer formation, right? We'll have the boundary layer formation. So when this boundary layer formation is happening, we'll have the boundary layer formation across your entire periphery of your intake. Will have the boundary layer formation. So as you know, when the velocity is getting decreased and if your pressure is getting increased, what will happen? Initially, if the flow is having sufficient velocity, you will have a attached boundary layer. Okay, but if the pressure is keep on getting increased and momentum is getting decreased, what is going to happen is that the momentum of your flow or velocity of your flow is reduced, means the flow will not have sufficient energy or momentum to move forward against this increase in the pressure. Right? So already your pressure is increasing. In nature, your flow will always move from high pressure to low pressure. But here, at the inlet, my pressure is less. As it moves downstream, my pressure is getting increased. So that means already your flow has to move against this high pressure. If the momentum of your flow is being continuously reduced, at certain point, the momentum becomes zero. And what will happen is that your flow will start moving the reverse direction. Okay, so when this once your flow starts moving in the reverse direction, that's when your flow is going to separate or your boundary layer is going to separate. Okay, you can ask, what happens if the boundary layer is going to separate, or why do we bother about the boundary layer separation in sense? Whenever the boundary layer separation is happening, you will have the formation of wakes and vortices. Okay, and one more thing is that when the boundary layer separation occurs, there is going to be a loss in the total pressure. Total pressure loss will happen. So, as we have already mentioned, the pressure recovery factor, that is P02 by P01, should be close enough to 1. Even if not 1, it should be nearly close to 1. If the total pressure loss is going to happen because of flow separation, what is going to happen? The pressure recovery factor of your intake will be reduced. Pressure recovery means the efficiency of your intake is being reduced. Okay, so what we have to do? We have to not only the efficiency of your intake is going to decrease. Okay, when these wakes and vortices form due to flow separation, when it is moving downstream, when it goes to the compressor, okay, there also it is going to create the loss. So loss introduced in the intake will propagate to the compressor also, which will result in reduction in the efficiency of your compressor also. That's why it is important to understand how does this stall is happening and how we can prevent it. Okay. So this is what, like, if the flow is turbulent or turbulent in sense your Reynolds number is very high, right? So if the flow is having sufficient momentum, obviously you will have high velocity, so Reynolds number also will be very high. So your flow will be attached with your surface. But if the flow momentum is getting keep on reduced, what is going to happen? Instead of flow moving in the forward direction, it will come in the reverse direction. So what is going to happen? You will have the low pressure zone or wake zone formation on the surface of your intake. Okay, this will result in the loss of your total pressure and formation of wakes and vortices. When the wakes and vortices, when they enter, the presence of this wake and vortices will create the unsteady flow. When the unsteady flow enters your compressor, what is going to happen? It may introduce the stall in your compressor. So it is mandatory to prevent this stall in your intake itself. Okay. So under what condition this stall is happening? It's not like all the time you are going to have these stall. When you are going to have this stall, just like in your airfoil, when we used to have this stall is that during high angle of attack operation and low speed. So under higher angle of attack, alpha is very high and the velocity is very less. During this time only, in your airfoil also you will have the flow separation problem, right? So here, similarly, when we will have this high angle of attack and low speed operation, basically during your takeoff as well as during your landing. Especially during your takeoff, your velocity is very less and your angle of attack is more. That's the time your flow separation happens in your airfoil or wing. Similarly, in the intake also, during your takeoff only, we will have this flow separation problem, because during your takeoff, your momentum is already very less because your flight speed is less. Okay, if the initial momentum itself is less, when it is decelerated, when it is passing through your intake, what is going to happen? Its momentum will be further reduced, which will result in the flow separation. So we can clearly understand that separation or stall of your intake occurs during your low speed operation, that is during your takeoff as well as during your landing. So you can see here there are 4 different situation happens. Okay, for example, there are 2 reasons why the flow separation will occur. One is due to the less momentum. Another one is due to the design of your intake itself. Okay, so design of your intake in sense, for example, if I have an intake, so this is having, say, your area at the inlet and area at the exit, AI, AE. You see, the angle here is much greater than angle here, right? If the area ratio is same, but the angle is very high in this case. That is, if you are having a very shorter intake, what is going to happen for the given area ratio? Your angle is going to be very high. Okay, so if the angle is going to be very high, what is going to happen? The flow separation will occur easily compared to the top, the intake which is having more length. So there are 2 sources of flow separation. One is maybe it may be due to the inlet condition of your flow, or it may be due to the design. Okay, so you can see here well behaved flow in sense there is no flow separation. Your flow is moving parallel to your wall. Okay, so large transistor stall means basically it may be due to the local flow separation. Okay, that is because of lost in the momentum. If you are not going to control this, transistor stall will become steady stall. Okay, And what is this jet flow in sense? In the intake, where you will have a very rapid increase in the air. In those situations, what is going to happen? You will have the jet flow. Jet flow in sense, you will have the vortices formation. Okay, at the center portion only, you will have the flow movement. Okay, basically, what is going to happen? This is going to reduce the amount of mass flow rate enters inside your compressor. Right? If the mass flow rate of your air reduced, means what is going to happen? Ultimately, the thrust generated by your aircraft also will be reduced. So, the stall, whenever the stall is happening, what is going to happen? The mass flow rate entering inside your engine will be reduced. So, the stall not only increases the total pressure loss, not only increases the loss in your compressor, it also creates the loss in your thrust. Okay, so it is very, very important to design your intake in such a way that you won't have the problem of this jet flow formation. So you can control this transitory stall by providing or by energizing your boundary layer. Right, similar to the method we use in the airfoil or like wings. You can use the similar kind of technique in the intake also to energize your boundary layer. As long as you energize your boundary layer, it won't separate. But this jet flow formation will occur if we are having a intake which is having a rapid increase in the divergence angle. Okay, so in order to prevent this, we have to change the design of our intake itself. So till now we have just discussed about what is the requirement of your intake and what is the subsonic intake and what is its function. And later we have seen what is happening across your intake and how does this stall is happening, and levels of our different under what condition your stall is happening, all we have discussed. Now we are going to see uh, type of pitot intake. In sense, this pitot intake is the most commonly type used intake in our gas turbine, or that is in your aircraft application. That's why we are gonna just see about only the pitot intakes. So what is this pitot intake? In sense, it's like, you know what is pitot tube, right? A simple duct in which the flow will enter. Your intake also is kind of similar to this pitot tube. That's why we call this as the pitot intake. Okay. So this pitot intake, we have three types of pitot intake. One is a ported intake, a integrated intake, and then flush intake. Okay. So this ported intake we use in different aircraft, integrated intake we use in different aircraft, and flush intake we use in the different applications. Okay. So ported intake in sense is kind of simply an open duct straight to your incoming flow. Okay, and this is the most commonly used intake in our commercial as well as defense or military aircrafts. Okay, for example, you have the turbofan or turbo jet engines you are having, right? So turbofan we use in the commercial aircraft, and turbofan we use in the turbofan we use in the commercial aircraft, and turbojet we use in the fighter aircrafts. Okay, so in these two intakes we have in these two engines we have this ported intake. Okay, where your flow will simply enter. Okay, where the flow will be decelerated. Okay, so if you take a typical ported intake, what is the source of losses? Basically, it is going to be separation rather than your frictional loss, because when your friction will happen, if the length of your wall is very high, or if the contact surface of your fluid and your solid wall is more and more, means you will have more amount of frictional loss. Whereas in case of your ported intake, the length of your intake is very small. As such, you can say the loss created due to friction is significant, but the major loss or major source for your loss in your intake is going to be flow separation. Okay, so you can get as much as 100% pressure recovery factor, that is close to that of 100% pressure recovery factor for your ported intake. And next one is the integrated intake. So what is this integrated intake? In sense, here the body of your aircraft, okay, as well as the portion of your intake will be integrated together, or you can say the part of your aircraft itself will act as an intake. For example, you see your fighter aircrafts, you won't be able to see the engines outside, right? Have you seen any fighter aircraft, that is supersonic aircraft, where you are having the engine outside? Means no, because your engine is kept either inside your fuselage or inside in the like it's built inside your mostly you'll have your engine inside your fuselage, right? So that means since the engine is already fixed inside rather than hanging outside, compare in case of your commercial aircraft, you can see your engine is outside, whereas in your fighter aircraft, your engine is kept inside. Okay, so that means you have to take this air towards your engine. So inlet like opening will be provided. For example, in some aircraft, you can see at the bottom or side of your nose cone location, you can see a hole is provided. Basically, that hole is the source of your flow to your engine. Through that hole only, your flow will be entering towards your engine. So in case of your integrated intake, the major loss is going to be friction, because here from your nose location to inside your engine, you have to take this flow through a large passage. That means your frictional loss is going to be more compared to that of your flow separation loss. Okay, next one is the flush intake. Flush intake in sense, for example, just you won't have any protrusion outside. On the surface, you will have an opening and your air will be entering inside. Okay, so this flush intake mostly we use in the missiles, that too in the air breathing missiles. So you can ask in the missile, where do we have the air breathing missile instances? In an missile which is fitted with ramjet engine, basically they are the air breathing missiles. Most of the missiles are non-air breathing. It's kind of similar to rocket, but few missiles are fitted with the ramjet engine. So for that ramjet to operate, obviously you have to take in the atmospheric air. So in those situations or in those conditions, we use this flush type intake, okay, to take the air from your atmosphere towards your engine. Okay, so these are all the three types of pitot intake. One is podded, another one is integrated, last one is the flush intake. So your podded intake is used for subsonic aircraft, that too commercial, and it may be a fighter, but not fighter in sense military applications where your aircraft, cargo aircraft, where you will have the subsonic. So your podded intake basically used for subsonic application. Your integrated intake is for the supersonic application. Flush intake also used for the supersonic application, but only difference is that flush intake is for missiles, whereas integrated intake is for the fighter aircraft. So the last portion we are going to see in this today's lecture is the operation modes of a subsonic inlet, or how does this inlet is behaving under different flight conditions. I already stated this inlet has to provide sufficient amount of mass flow rate to the engine, okay, irrespective of its flight condition. So flight condition is that it is during your ground operation, that is still, during your takeoff, during your cruise, during your high speed. So irrespective of this different speed or different flight condition, it has to continuously supply the required amount of mass flow rate. So how does it is supplying the required amount of mass flow rate? You know that you take a duct, a constant area duct. If you keep it still, there won't be much of air will be passing through. But when you start moving this duct, what is going to happen? Air will be entering. The higher the speed you are moving, more amount of mass flow rate will be entering, right? But here we have a different condition in aircraft, that is low speed operation, design speed, and overspeed. So during these different conditions, how do they continuously supply a required amount of mass flow rate? That's what we are going to see in these operation modes of subsonic inlet. Okay, so here I have just shown you the schematic of a podded intake. So we are just going to take an intake which is most commonly used in the commercial aircraft. Okay, so let us take a first case where my aircraft is still, which is in the ground. Okay, now I'm going to start my engine. So once your compressor starts rotating, if you say if the engine is still, how does your air is entering? Because we rotate the compressor. When your compressor is rotating, what is going to happen? it is going to suck the air from your outside. Okay, since your air is still, the air from entire throughout the surrounding atmosphere will and move towards your compressor. So before it goes to the compressor, it will pass through the what to say uh, your intake, right? So we have something called a capture area here. What is this capture area in sense? The area by which is influenced by the operation of your aircraft, or you can say from the cross-sectional area from which your air is being taken inside your engine. That's what we call it as the what to say capture area. Okay, so if I'm going to take a low speed operation, that is like a still operation, aircraft is still, that means air from your entire surrounding will come towards your engine. Okay, so when you take the capture area AC compared to your inlet, what is your AC is much greater than area of your intake. That means what is happening? Here area is more, the intake area is less. That means it's kind of similar to the convergence section. As you know, flow passing through the convergence section, it will be accelerated. So during your low speed operation or station, like still operation, what is going to happen is that the flow will be accelerated outside of your intake. Because of this acceleration, what is going to happen? You know, mass flow rate m dot is equal to rho a v. So the velocity is being increased. So obviously, the mass flow rate also will be increased. That is how during your still operation, the sufficient amount of mass flow will enter inside your engine. Okay, it's kind of like this is what we call it as the external acceleration. Okay, before your flow enters your intake, the flow is being accelerated. But once it enters the intake, it will be start decelerating. Okay, but outside it is being accelerated. That is due to your capture area is being greater than your inlet area. Okay, now if you start moving your aircraft, that is, it is going to take off. What is going to happen? Your flight speed is getting increased. When the flight speed is getting increased, what is going to happen is that the capture area will be reduced, but still it will be greater than your capture area will be still greater than your inlet area. So once again, during your takeoff also, you will have the external acceleration. So this external acceleration will be sufficient enough to supply the required amount of mass flow rate. Okay, now let's say I'm going to fly my aircraft during cruise. So obviously during your cruise operation, you will fly your aircraft at a design condition. So what is the meaning of design condition is that at that condition, your aircraft will have the maximum efficiency, or the components are designed for that particular Mach number. At that particular Mach number, they will operate efficiently. Okay, so during your cruise, why do we consider the cruise speed as the design Mach number? Is because during your cruise only we will travel for more distance, or during takeoff and landing is a very small portion of your actual flight. Okay, cruise is the important one, so we should have the maximum efficiency during your cruise. So during your cruise, what will happen is that your capture area will be either equal to your inlet area, or it will be less than your inlet area. So less means, equal means there won't be either any acceleration or deceleration. Your flow will be just entering as it is, and it will be decelerated through your intake. But if your capture area is smaller than your inlet area, what is happening here? It's kind of like a divergent section. So what is your flight speed? It is subsonic. A subsonic flow entering a divergent passage, what is going to happen? The flow will be decelerated. Okay, so because of this deceleration, what is going to happen? Your intake will not choke, or else what is going to happen? Your intake will choke. Okay, so because of this external deceleration, or during your cruise, either it will decelerate or it won't decelerate. Okay, and during your top speed or maximum speed operation, what is going to happen? Your capture area is going to be much smaller than intake area, which will result in huge amount of external deceleration. Okay, and when the flow is decelerated very high amount in the outside itself, what is going to happen when the flow enters? It will have more amount of pressure rather than movement. Okay, so because of this, there is a possibility that your flow will easily separate. That's why, even if you are having a sufficient amount of thrust, if you are going to overspeed, okay, you will have a huge amount of loss. That's because of the flow separation occurs in the intake. Okay, so that's how, by whenever we are operating at different operating condition, the capture area is varying accordingly. So you will have either external acceleration or external deceleration to continuously supply the only required amount of mass flow rate. Okay, so these are only four cases where our aircraft will usually fly. One is the still or ground operation. Second one is the during our takeoff. Third one is during our cruise, and fourth one is during our high speed operation. Okay, so this is the operation modes of our subsonic inlet. So with this, I'll finish this today's lecture. So what is that we have discussed in the today's class? We have just gone through what is this intake and what is the requirement of intake, and then we have seen what is subsonic intake and what is the function of the subsonic intake, and later we have seen how does the flow or what is happening across your subsonic intake, how do they behave, and then we have seen the stall, how does the stall is happening. Okay, and different internal flow inside your intake we have seen, and what is the reason for the stall also we have seen. And later on we have discussed about the different types of pitot intake. Okay, where we use the different types of pitot intake, and then we have discussed about the operation modes of sonic intake.
Like, share and subscribe. Hit the bell icon for more updates.